All right, so in the first unit we did limits, and we learned the definition of the derivative. And the definition of the derivative, when you try to find a derivative, generally takes 5 minutes. And now we're going to shave off about 4 minutes and 59 seconds off of those 5 minutes by learning some of the rules of calculus and derivatives. Here's our first rule, which is the power rule. So imagine you had to do all of these with the definition of the derivative. Like, that's where you have to plug in that x plus h and simplify until the h cancels out. And some of these would be rather long, like the x to the 4 and the 4x to the negative 3. But if we looked at these and we started looking for a pattern, okay? So let's say we did the definition of the derivative for each of these, and you got this one to be 2x, and this one to be 3x squared, and this one to be 4x cubed, and this one to be 9x squared, and this one to be negative 2x to the negative 3, and this one to be negative 12x to the negative 4. And that's about how fast we can do the derivatives if we can recognize a pattern. Okay? How long did it take me to write those answers? Not very long. If I'd used the definition of the derivative for each of them, we would be here at least for another half an hour, even if we did them quickly. So the question is, can we see a pattern in what's happening? Is there a pattern that happens with the numbers? Is there a pattern that happens with the exponents? And you already know, so I'm not even going to let you answer, because that would be cheating. Yes. What do you see? The exponent that was seems to be multiplied, like these ones have a coefficient of 1. Here we have a coefficient of 3. It got multiplied by the 3. Here we had a coefficient of 4. It got multiplied by the negative 3. So that seems to explain the number out in front. And then how do you explain what happened with the exponents? They just go down by 1. And this is the power rule. If you have a power, that exponent could come out in front, multiply whatever's out in front, and subtract 1 from the exponent. And how much quicker does this, imagine with the definition of the derivative. Oh my goodness. You have an x to the 51. So you have to do x plus h to the 51 and multiply it all out, only to have everything cancel. And then your derivative will be 51x to the 50. And this rule doesn't just hold for regular powers. We can play around a little bit with some other things as well. For example, square root of x. Can you see that if you temporarily rewrite this as an exponent, x to the half, then the derivative, you bring the half out in front, subtract 1 from the exponent. And I'll tell you that one of the things you are going to get really good at in calculus is subtracting 1. It's like, ooh, you might have felt I was pretty good at that already, but you're going to really get good at subtracting 1. This one's interesting. Could you write this as an x with an exponent? Technically, you could write it as x to the 0. And if you followed the rules, what would you get? 0. Because the 0 would come out in front, multiply the 5. And even though you would get an x to the minus 1 after that, you would still get 0. Seven x. Technically, you have a 7x to the 1. Technically, you would get this, right? Which is just 7. Now, if you think about 7x, that's a straight line. y equals mx plus b. What is the slope of y equals 7x? 7. And if you drew a tangent, a straight line, the tangent to the straight line is itself. No matter what point you put it on, the slope of that line is always 7. So it should make sense that a line with a slope of 7 would have all of its tangents also have a slope of 7. Here with a cube root, you would change your cube root to x to the 1/3. Then you could bring the 1/3 out in front, subtract 1. That's a tricky subtract 1. And get negative 2/3. And finally, with the last one, if I'm going to use the power rule, I have to be able to rewrite it as a power in the form that the power rule works. So I have 1 over the square root of x. That's the same as 1 over x to the half, which is the same using your negative exponent rule and x to the negative a half. And now I have x with a power. I can bring the power out in front and subtract 1 from the exponent. Some of these ones, if we used the definition, would have taken us even longer to do. I can imagine that last one taking quite some time, or the cube root one being a little bit more difficult. How would you do this one with the definition? It's kind of an interesting one to do with the definition. So if I did the limit as h goes to 0, what happens when you plug x plus h into 5? You still get 5 minus f of x, which is 5. And it's a little bit weird there, because you get 0 over 0. So it's like, can I really say it's 0? Or should it be something else? If you think about it graphically, what does y equals 5 look like? It's a horizontal line. What's the slope of that line always? It's always 0. So it might, thinking of it that way, be able to say, I know that the derivative is equal to 0. So here it is, your constant rule and your power rule. The derivative of any constant is always equal to 0. Yes, sorry. Mathematicians are notorious for not wanting to write things down. They like to shorten things, okay? And so there are some symbols that you've already learned, right? You've learned stuff like x belongs to all real numbers, because if you had to write that as a sentence, it would really annoy you. So there are some symbols. Now, this is the symbol for all, because it would take forever to write those 6 letters in for all. We would like to make up, right? So instead of having to write for all real n, I can write this, for all n belonging to the real numbers. Do you want to know some of my favorite math shortcuts? This is one of my favorite. If. Do you know what that stands for? It stands for if and only if. Really if. If and only if. You put an extra F on there, right? Right? Like here, I will. No, if implies a single, but if, and then it means no other conditions can be allowed. If and only if. It's really ifing it. right? For example, x squared equals x. Well, okay. Is different than this is not, this is true. This is not true. Okay? So that extra F, super important in some cases. There's a good example of where one if is still true, but the if and only if, the if would not be true. Yeah. So there is some mathematical shortcut language. And if you get into higher level math, not if and only if, because there's other places where it may come in handy, but if you get into higher level math, then you'll have to do a bunch of proofs. And when you're doing a bunch of proofs and having to write some of these things often, then these shortcuts become nice. Okay. So the power rule, do you see how this works? That the exponent of the n came out in front, and then you subtracted 1 from the exponent. And now we can save a ton of time answering questions. Okay? Next rule. Constant multiple rule. If you have a number in front of a function, you can find the derivative by just finding the derivative of the regular function and multiplying by that number. So this one, for example, if I have 5x cubed, technically the derivative of the x cubed is 3x squared. And then that 5 could just stay out in front. Okay? None of you are ever going to write this, because what's 5 times 3? It's 15. You're going to immediately say, oh, I'll bring the 3 out in front. 3 times 5 is 15. I'll subtract 1 from the exponent and be fine. But the constant rule is saying that this is true of all functions. If you have a number in front of some function and you can do the derivative, that number would stay out in front and multiply by whatever that individual derivative was. Which these rules are important because sometimes in our details, we need the rule and how it works and say, okay, I'm allowed to do this at any time. But for the most part, as far as practicality, you're going to just learn how to use these straightforward. You bring the 3 out in front. 3 times the 5 is 15. Subtract 1 from the exponent. Okay. And in the questions I have here, we're going to get used to all the different sort of forms of asking the same question. So this one has the DYDX. That's another way of writing the derivative. So if the question says find DYDX, then in your answer you should write DYDX equals, and 5 comes out in front, subtract 1 from the exponent, negative 15x to the 4. And this is kind of an interesting crossroads because I think you have to go back to grade 9 where you had math questions where they asked the question, you could just write the answer and then be like, yeah, I'm done. Like you think grade 10, grade 11, grade 12, like some of grade 12 math, you had to learn so much writing to get your answer. In grade 9, they still had like x plus 3 equals 5, and you could just like, oh, x equals 2, write your answer right away. So it's kind of interesting that the beginning stages of derivatives is that quick. Here's a medium level one. In a medium level derivative question, and here the wording of this question says, differentiate with respect to x. So it just wants you to find the derivative. So as far as your answer, you could choose any form. I'll go with DYDX. But I might first take this equation, and it is a medium one because as a first step, I would take that x to the 8, which is in my denominator, and move it to my numerator. Because that's where your power law works. And can you see that that's the same as just writing 3/4 x to the negative 8? And once it's in that form, so this is what makes it a medium one, now we can bring that negative 8 out in front. Negative 8 times 3/4. Negative 24 over 4. Subtract 1 from the exponent, you get x to the negative 9. You can simplify this. To negative 6, x to the negative 9. So this is a medium level one because you had to do some algebraic manipulation first to get it into the power rule form. And that's a lot of stuff that we're going to be doing in this course, is figuring out how to manipulate things so we can do the derivative. Here's another just form of asking the derivative. This d over dx of whatever's in brackets is saying find the derivative of what's inside. So you can write either dy dx for your derivative. Here the 4 would come out in front. Subtract 1 from the exponent. 28x cubed. And the hardest ones involve all of your exponent laws that you've learned in the past. We need to change that cube root of x squared into the form so that we can use our power rule. So first of all, are you okay that a cube root is like an exponent of a third? Technically, I skipped a step. Here, I'll do it really slow. I would have x squared to the third. And then you have to know your exponent rules for what happens when you have a power to a power. You multiply. So I would have 2 over 1 times 1/3. So now I've got x to the 2/3. Which, if you did that immediately from the initial one, perfectly fine. If you can do that mental math in your head and put them together, that's perfectly fine. Is it in the form yet? No, because our power is in our denominator. So we have to do one more step. Move it to our numerator, which will give us an x to the negative 2/3. And now, notation-wise, I'm going to change this to the derivative notation. Now I have a single power. I can bring the negative 2/3 out in front. Negative 2/3 times 7/3 will give me negative 14/3. Negative 14/9, sorry. Subtract 1 from the exponent, and again, this is where I said you're going to get really good at subtracting 1. Right? How do you subtract fractions? Need a common denominator. So subtracting 1 is like subtracting 3 over 3. And we get negative 5/3. All right. How difficult is the power rule? Not too bad. The hardest things is when it takes and it reviews stuff from grade 9 exponent laws. Those are the hard ones. So we need to know all of our algebra from previous years will come into play because we're going to have to manipulate things. What if I gave you the answer? What was it originally? So we have DYDX, so we'd write y equals. Well, you know that you had to subtract 1 from the exponent when you do the derivative. So does it make sense that there would have had to have been a 5 as an exponent to begin with? And then what number had to be in front? Well, I mean, you can write a 1 if you'd like. But working backwards, that's what you would get. Try this one. Some of you have done it already. And you know you'd have to have an x cubed if it went down by 1. What number would have to be in front to get the 12? It'd have to be a 4. All right, there are some practice questions here, but we're not going to work on them right now because I don't feel like you've learned enough yet to really feel like you need to do some practice. We'll go some more rules. So probably the hard thing that you're going to find about derivatives is there are a lot of rules. We're going to learn a number of rules to provide us with shortcuts so we can do derivatives faster than having to use the definition of the derivative. Now, when you go to university, most of you, if you go and study something with mathematics and you take a calculus course, they are going to actually ask you to prove the derivative rule. So, for example, the power rule, you would start off with any power like this. And then you would have to use the definition of the derivative, limit as h goes to 0, x plus h to the n minus x to the n all over h. And you would have to develop this and figure out what's going to happen. I won't be. I'm just giving you a heads up that that'll be one thing that's a little bit different than a calculus course in high school and a calculus course in university. The university would get you to prove this. So here you'd have to use Pascal's triangle and say this will be the limit as h goes to 0 of x to the n plus x to the n minus 1 times h plus, and there'd be a number in front of that. There'd be an n in front of that from expanding it completely using Pascal's triangle. Plus dot, 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 until you subtract your x to the n all over h. And then you'd be able to argue that these ones would cancel out. And all of these other ones have h's, which you could factor out. And only the first one has a single h. So all you would be left with is the n times x to the n minus 1. And since you've proven it for a random number n, you therefore prove it for all numbers and all exponents. The sum and difference rule. This is a nice intuitive one. What do you think the derivative of x squared plus 3x minus 7 is going to be? Okay. Pencil it off to the side, what you think it would be. The answer is 2x plus 3. And I'm going to show you what this really looks like in an app. Oh, and thanks for the new desktop. By the way, what's funny is they put it on, I don't know if any of you noticed it. They put it on as a joke, right? As a funny answer that the person thought the original one was an 8 written sideways, and so we'll write the 5 written sideways. But what I find also interesting, and I don't know if any of you noticed it, but this limit that they gave as the if is actually wrong. It's a does not exist one. Because if you come from the left side and you come from the right side, one of them is infinity and one of them is negative infinity. So I think, given the fact that they gave a wrong answer for the first one, this second answer of a sideways 5 is brilliant. Really like that. Yeah, I got to my computer this morning. I'm like, someone hacked me over the weekend. And I was like, what happened? And I did very poorly on each of them. Only to realize, yes. I thought back, what? Oh, yeah, missed it all. Figured it out. Anyways, what I was going to show you is if open up. Here's a little program that I wrote in Geogebra. I don't know if you've ever heard of Geogebra. Geogebra is a free online graphing program. Maybe not as intuitive as Desmos, but really quite powerful. And if I write in the equation that we just had, x squared plus 3x plus 7, is that it? Minus 7? Oh, shoot. X squared plus 3x minus 7. I'll zoom out here. That would be a parabola. So graph the parabola right away. Now, according to what we found, the derivative of this should be 2x plus 3. Now, the way that I've got this program designed right now is I've got a tangent drawn. It happens to be drawn when x is 0. The program automatically calculates the slope and plots it. So apparently, when x is 0, the slope of the red line is equal to 8. If I drag up this point along, here, can you see my slope? Come on, drag. Oh. Okay. A little bit of frustration right now because I should be able to take this point B and drag it, but it's not. It's not letting me, which totally ruins what I was about to show you because the program is not letting me draw it. What I wanted to show you is I could drag this point B along the parabola, and as I would draw it, it would plot all the slopes, and the slopes would perfectly make a line which has an equation of 2x plus 3. So I'll get that fixed for next class so you can actually see it because it's quite nice. So what is the sum and difference rule? If you are adding and subtracting different functions, you can take the derivatives of each of those individual parts separately to find your derivative. Try these two. I'll put the answers up in a second. Try these two on your own. I'll put the answers up in a second. All right, how do you do on the first one? So for the first one, f prime of x, the derivative, you would use your power rule for the 8x squared, and you would get 16x. You do the power rule for the 3x, and you would get plus 3. You do the power rule for the minus 4, and you would get 0. So you wouldn't have to write it. And this would be the derivative. For the second one, new notation for a function. So again, just trying to introduce you to weird notations. This is saying the function f takes every x and maps it to this equation. Okay? As far as writing the derivative, we'll just write the derivative in the normal form. I would bring the 2/3 out in front. 9 times 2/3 is 6. Subtract 1 from your exponent. Plus, bring the 1/5 out in front. 10 times 1/5 is 2. Subtract 1 from the exponent. -4/5. So again, what's the hard part here is subtracting 1, right? And multiplying by fractions. Is it wrong if you first did 9/1 times 2/3 and wrote 18/3? No, it is not wrong. So the straightforward ones are things are added and subtracted, and you're able to take the derivative. Now, derivatives are fussy. If you don't have a rule for the derivative, you can't make up your own rules. That usually, I know, it's like logarithms. In logarithms, you have your main rules for logarithms. If you try to make up new rules for logarithms, things go bad quite quickly. You're like, I don't know my rules for logarithms. Well, then it can just go bad altogether. This is one that's not in a form right now that fits any of our rules. How can we manipulate this so it does fit our rules? Right? Well, squaring means multiply by itself. If I multiply this all out, x squared times x squared, I'd get x to the 4. Minus 4x squared would give me minus 8x squared. And minus 4 times minus 4 plus 16. So by multiplying it out, I now have individual powers that are being added together. Derivative rule for individual powers. And since the question said DYDX, that's why I use that notation. If the question doesn't provide any directive, you are free to use any notation. So, bring the 4 out in front, subtract 1 from the exponent. Bring the 2 out in front, subtract 1 from the exponent. I wouldn't have to write that little 1. And derivative of 16 will be 0. So our final answer is going to be 4x cubed minus 16x. Yes? We could. Yes, this could be a chain rule one once we learn the chain rule. Right, well, in this last one, if you wanted to rewrite this in a different form, okay, and you'll find that your textbook sometimes writes the answers in factored form. For example, this is equal to, I could pull out a 4x, leaving me with x squared minus 4, which I could factor even more. So yes, you can bring out a 4x, but where do you see the 4x to come out of here? Is it because of this 4? Is it because of this 2 and this 2? Where does it come from? Well, it's a negative 8x squared when we see it here. But the question is if we used a new rule to go from here to here, how would we see it? And it's going to come. That's a chain rule. That's That's like a week away. Maybe not even. The chain rule is not as intuitive as the power rule. Power rule is really straightforward to start off with. Manipulate this one so it's in a form that we're able to do it. An interesting thing about this one, for those that you already know other rules, this is one, there's another rule called the product rule that you could use, but I would actually argue that simplifying it is easier than the product rule. So I could change the cube root to next to the 1/3. It's still not in a form that I'm able to do the power rule and the sum and difference rule, because I'm still multiplying. I only have a rule for adding and subtracting. I could distribute, but now we have to go back to our grade 9 exponent laws. What happens when I do x to the 3rd times x squared? What's the rule for multiplying powers with the same base? You have to add the exponents. So in your notes, so that you don't forget this, I'll write 2 plus 1/3, and I'll write plus 3, 1 plus 1/3, because I would add the exponents. And then in order to add exponents, you need a common denominator. So is everybody okay if I do the 2 as 6/3 in my head? And then 6/3 plus 1/3 will be 7/3. And the 1 in my head is 3/3, so I will get x to the 4/3. And we did all of that initial just to get it into this form. And now that it's in this form, I can find the derivative. Y prime will equal, oh, it says find DYDX, sorry, I'll write DYDX equals, bring the 7/3 out in front. You can write 42/3, or you can simplify it to 14. Subtract 1 from the exponent. 7/3 minus 1 is 4/3. Plus, bring the 4/3 out in front. You can either write 12/3 or 4. Subtract 1 from the exponent. And there we have the derivative. So here it took actual more work just to set it up. The derivative part is a single step. Okay, try this one on your own. See what you can do to manipulate this one. Using the rules that we have. Yeah. Yeah, but you don't know the quotient rule yet. How do we use the rules that we have? How do you manipulate that equation? And I want to see if anybody comes up with different algebraic manipulations. Oh, nice. Say, I want to play around with your algebra. Try and manipulate that. Yep. That will work. Okay, let's see how you did. Method number one. Method number one, I'm going to use unadding fractions. You know how to add fractions? You need a common denominator. So if you unadded fractions, you'd sort of work backwards and say, well, right before this step, they had to add these two fractions together. This is what I call unadding fractions. Doesn't that make sense? You just unadded the fractions that were added together. Then, can I simplify the first one? Yes, it would become 2/3 x to the 6. Can I simplify the second one? Well, 9 divided by 3 is 3. And I have an x onto the bottom. What can I do with an x on the bottom? I can change it to an x to the minus 1. And from there, I could do the derivative, bring the 6 out in front. That'll give me 4. Subtract 1 from the exponent, bring the negative 1 out in front. That'll give me negative 3. Subtract 1 from the exponent, and I'm done. Method number one. Method number two, I like the unadding fractions one. I think it's quite easy to see what's happened, but it's interesting that your brain, if I ask you to add fractions, you'd have no problem, but probably no one has ever asked you to unadd fractions. And so your brain has a little stop there, and you missed maybe seeing that technique as a result. Second way is you could change the x to an x to the negative 1 and bring it to the top. And then you could distribute your x to the negative 1 on top and get 2x to the 6 when you add those ones, plus 9x to the minus 1. Then the dividing by 3, you could think of as multiplying by a third. And then when you distribute that third, you get the same thing, and then the derivative is identical. I like the unadding fraction one. I think it's a little bit more intuitive as far as what we've done there. But we played around with our equation to get it into a form that we could do the derivative. And a lot of this course is that way. Can you manipulate things and switch things around so that you can play with them and work with them? Okay, work backwards. Come up with an answer or a question that could have been there originally. All right, working backwards. Did you find out that it had to be an x to the 4? And the number in front there would have had to have been a 5. And did you see that you would need a 5x? Awesome. And did anybody include 72.3? No? You put 7. Is 72.3 wrong? No. Is 7 wrong? No. If you didn't write anything, would that have been wrong? No. So later on, okay, again, the nice thing in this question, when we read it carefully, it says find a function. So this is your opportunity. Do you have, Lily, do you have a favorite number? 13. This is your opportunity to include that 13 in the question. You're like, oh, I can put 13 in this question. If you're feeling like 13 has been discriminated against, underused, oh, you go into another hotel, it's missing that floor, it seems unfair that it's been underused in the world, and so now here's your chance to include the number 13 if you wanted to. Later on, when we do these ones more formally, we're going to just go plus c and say c can be any real number, because anything would work. Okay, but for right now, it just said find a function, so anything would work. You could leave it blank, or if you wanted to, include your favorite number. And I'll try to be more inclusive of 13 this year as a result. Okay, you can include that number in there. Okay, so take out your textbooks. Now there are 2 sets of questions, and one of the things that your textbook is going to do so well for you this year is it is going to improve your algebra skills. So when you get an answer, like for example, if we go back to this answer that we got in A, I got the answer of 4x cubed minus 16x, which is correct. But look at the answer key, because the answer key in this textbook will often factor and simplify. So after you get your answer, make it like a little challenge. Can you manipulate, if the answer key had this, could you manipulate your answer and get what the answer key has? And that's where your algebra skills are really going to take off and get stronger and stronger and stronger.